Hi, everyone. Thanks for joining today. You've heard, you're still in the vision track, and in the next few minutes, we're going to be looking at some known problems in vision models, specifically adversarial examples. Actually, you might have already seen this image going around for the last few years. It was very popular. It's taken from the Ian Goodfellow paper from 2014, where he and his colleagues explained how to perturb or attack an image of several different images. In this case, it was a panda, which after having some slight noise, perturbation superimposed, fooled a neural network into thinking that it was actually a gibbon. Now, in the next few years, there's been a lot of activity. Whoops. So let me try to get this video going. And the same effect was taken to real life. So if you take a look at the video, this is originally a 3D printed turtle, which without any kind of perturbation is correctly identified as a turtle. However, this team a couple of years ago was able to 3D print an adversarial turtle that was systematically identified as a rifle by an inception model trained over ImageNet. And it wasn't just a one-off angle, it wasn't a cherry-picked way of seeing the turtle, it was actually consistently, no matter what angle it was pictured from. Now, in the next few minutes, we're going to talk about what these adversarial examples are, whether you should be concerned and how they affect you, and if you want to use them to your advantage, how you can do so. So, why am I actually interested in them? I'm a computer vision engineer by trade. Most of my background has been in medical imaging, but for the last couple of years, I've been working in autonomous driving and similar systems at Siemens Mobility. So medical imaging and autonomous systems, that's two fields where adversarial examples are likely to have a huge impact. Now, what are they? So I'm going to dive into a couple more examples also that could affect mobility. You can see here an example where instead of adding slight perturbations, a team last year was able to fool neural networks in real life by sticking certain fake pixels, so to speak, on a stop signal, for instance, making the classification say it was a 40 mile per hour signal. Now, it's not just classifiers. You can also see the same effect on detectors. So this year at CVPR, another team was able to fool, this is a YOLO V2 detector, and by printing a poster that was held in front of that person, they were able to bypass the detector. So if you're interested in privacy, if you're interested in surveillance systems, this is something you might want to look into. I think it's actually become already a t-shirt. If you take a look, you'll notice how as soon as the guy turns the poster around, he is again detected. So there you go. He's now going to turn that poster around, and you'll see how YOLO again sees him. If he gives it to his colleague, then he is again detected, but his colleague isn't. But it's not just RGB, actually. I'm going to show you a video where you're going to see the expected behavior in LiDAR. You're going to notice how there's a regular box placed in the middle of the road, and then it will be highlighted here as soon as it gets detected. So as you can see, we do have a box detected here, and you'll see in a minute what happens when the team places, instead of this benign box, one that is adversarially generated. So you'll notice how there's a different box being placed, and in no case is it detected here. Now you can think about the implications this might have in autonomous driving, for instance. But it's not just that domain. In healthcare this year, there's been a paper where they generated the same kind of examples. So again, adding some perturbation to the original image. They tried it with pneumothorax. They tried it with a melanoma. So the originally healthy image was perturbed, and they obtained a misdiagnosis of a melanoma. And the inverse also worked. So they took malignant images, superimposed some perturbations, obtaining a diagnosis of a healthy case. Now, what's going on here? What's happening? The very simplified explanation is if you have a classifier, the goal is to have this decision boundary that allows you to tell whether a sample belongs to class A or class B. And what an attack is actually doing is trying to force a sample from class A with the minimum effort necessary so that it goes squarely into the space that will make it be classified as being class B. But how do you do this? Actually, one of the simplest method to do this, the fast gradient method, is very similar to how you train neural networks. So if you're familiar with them, you've heard how the idea is you feed a stack of images into your classifier iteratively, and you expect to have a label at the end, and when that label is wrong, then you will have a loss that goes up. You take the gradient of that loss with respect to the weights. You backpropagate that because your goal is to tweak those weights little by little until that loss goes down again. And when it does, you consider your model trained. Now, the difference between this and an attack is basically two. One, you want that error to go up, not down, because you are attacking a model. And two, that model, you're not training it. It's frozen. You've already trained it. You're actually attacking a model that already exists. So you don't have access to it. And that's what this black model in the middle represents. You're not going to be seeing that model. But what you will want to do is tweak the input. So what you do is you take that loss, you take the gradient with respect to the input image, and that's the so-called noise that you're seeing. And now all you have to do is add that noise or that perturbation to the original image, and there you go. Now you've made yourself an adversarial example that you can throw at your model. So what kind of attacks are there? It's not just the fast gradient method. There's plenty of them, and you can look at them in let's say in two different dimensions. One of them being what you know about your model. The mildest attack being the one where you know nothing about the model, you have no access to the weights, you have no access to the original data, not even the loss function. And on the other side of the spectrum, you would have an attack where you know absolutely everything about the model. You may even have access to it, and you can optimize your attack over it. And somewhere in the middle are attacks that use proxy models to optimize. Another way of looking at the attack is thinking what the expected effect is. The mildest of them being one in which maybe you just want to reduce the confidence of the prediction. So for instance, for the case of privacy or surveillance systems, maybe it's just enough that the detector doesn't see me with a high confidence. Because usually in any vision system, you're going to be tweaking, you're going to have a confidence threshold. And anything that falls below that confidence, you think, well, it's a false positive, so we don't show it. So as soon as I manage to get a classifier or a detector to think that I'm a human, but maybe with just 20% confidence, I'm probably okay. Now, the next level to that is where you're not just reducing the confidence, but you want to have the wrong label being returned. So for instance, that case of the panda and the gibbon. You don't really care what the output label is as long as it's the wrong one. And then an increased malignancy of an attack would be where you're actually forging a label. So let's say I'm trying to forge documents, or I'm trying to cause chaos on the streets by making a classifier systematically think that a stop signal is actually a 40-mile-per-hour signal. So why is this happening? And there's bad news because there's no consensus yet in academia. So from what I've seen, there's a whole bunch of literature supporting different hypotheses, many of them reasonable, and there is no consensus. However, there's been one hypothesis that published this year, which is I'm very excited about it because, one, because of the implications it has, and two, because it's also very intuitive. And it's by Andrew Ilias and colleagues, who propose that the reason why this is happening is not because neural networks are faulty or because there's bugs. They are actually exposing features that are highly correlated with the classes, but it's just that humans aren't picking up on them. We're not seeing them. And the way they explain this is, well, let's imagine that, or actually there are some features that are very obvious to humans, and so, and you can perturb them to an extent, and humans will be able to see the differences. And there's other type of features that are extremely subtle, and neural networks can see them, but humans cannot. So some perturbations that you add to those features will make the neural network realize that a frog is no longer a frog, but the human will not realize it. So let's try this in the room. Let's imagine that this part of let's say this part of the room, from here to there, you're humans, and you're only going to be able to see the outline of this bunny. And from here to all over there, let's assume that you can see the full image. You're going to be neural networks, and you're going to be able to see the texture, the colors, absolutely everything about the bunny. Okay, so you folks can only see outlines. When you see a bunny, you see this. Okay? So can I get a show of hands who thinks this is a bunny? So sanity check. Oops. Okay. So I'm focusing on the humans here. Who thinks this is a bunny? Okay, confidence fairly up. That's good. So if I perturb that outline of the bunny, I can make all sorts of crazy things, but as long as I keep a rough shape of the two fluffy ears and the cheeks and everything, I'm going to suppose this is still a bunny. But let me check. Who thinks this is still a bunny? All of these are bunnies. Fairly confident. So I'm going to go back to the other image, and I'm going to perturb it slightly. So you are able to see everything. I'm not going to show it yet, but you're going to be able to see it, and you're going to see this. Is this still a bunny? Now you're cheating. No, you're not. Okay, so you still think this is a bunny. When I show you the feature that the humans aren't able to see, is this a bunny? No hands went up. Now, the humans were seeing this, and they were saying this is a bunny. The neural networks were able to see the full thing, and they're saying, hell no, this is no bunny. And that's the whole point of that paper. There are features that are really correlated to the class of a bunny. It's just that humans weren't able to pick up on them. So when you add perturbations to them, the neural networks realize that the image has changed too much for it to still be a bunny, or in this case of the paper, a frog. It's now something completely different, because that subtle feature has changed. Anyway, let's take a step back, because this is fun, this is really interesting, and it's a great read, but does it really affect us? Should we be caring about this? Because most of the time we're concerned about attacks, about hackers, and how fragile our systems are. But there's this saying that you should never attribute to malice what it's just plain stupidity. And when I say stupidity, I really mean, well, lack of diversity, lack of experience, lack of time, lack of money. There's all sorts of things you actually have to do to get your systems up and running, and you don't always have all the means that you need. So for instance, whenever you're building a system, you're going to want to design your data collection correctly. You need to go out and annotate it. You're going to have to, while you're training, design the correct augmentations. You're going to have to evaluate and test the hell out of your model before you put it in production. And you cannot always do this properly. And in fact, when you don't, things go wrong. So there's been crashes. There's been systems that were biased against certain specific humans. There's all sorts of things that go wrong. And it wasn't malice. It wasn't hackers. It wasn't adversarial examples. It was lack of time, lack of diversity, lack of many things. So what I'm trying to say here is, sure, adversarial examples are a problem. Hackers in the future might be a problem. But the very first stop should be, well, you need to robustify the basics of your systems, because that will make you fall a lot faster than a hacker will. In any case, let's say you're in a domain where adversarial examples are already an issue. Again, this is a whole bunch of things that you need to have covered. And let's say you design your data collection correctly, you've got all your data, you manage the annotations. There's two places where adversarial examples can help. One is during training, where you can augment the training data. So I suppose if you're working in Vision, you're probably already applying all sorts of augmentations. You're already flipping your images, changing intensity values, you're playing with contrast, you're adding noise probably. Well, an adversarial attack is only another form of augmentation you can apply. Why not? And then the way this would work is you take your vanilla training set, you put it through your adversarial toolbox, you generate a whole bunch of adversarial examples, and you feed them back into your classifier or detector or whatever it is you're training. And at least your model will already have been exposed to those adversarial examples. Now, this has the advantage that you don't need to really ask why the adversarial examples are happening. You can just go about it in brute force. You're giving your model a ton of adversarial examples so that it trains, and at least it can learn from them. But the problem is, how are you sure that you've got everything covered? You don't. You just don't. You don't know when to stop, and you can't know when to put your model in production. Now, another way of doing this, and they're independent, so you can actually apply both of them, is you can stress test using adversarial examples. So the idea would be there's tons of tools out there that already have the latest attacks, or you can implement them on your own. And you would take your testing data, again, put them through your adversarial toolbox, and systematically for each known attack, generate examples so that you can test your model and at least report which attacks had what effect. So at the very least, when you're trying to certify a model, or when you're at least trying to report to someone how good it is, you can tell, hey, we've identified that it's weak against this and this, but it's perfectly robust against this other thing. And the way you would do it is, well, this is an example, this again is my laptop, and what you do is, for each of those images that you're going to throw at your model, you generate that adversarial example, and you throw at it. And in this case, while I was playing with it, it was originally identified as a laptop with an 80% confidence, sorry. And then when I threw on it a perturbation that was supposed to be a stole, the result I had was that it was a prayer rug for 40% confidence. So at least I can tell whoever asked me that the inception model I was using to test this on is weak against an FGM attack with this kind of result. But I would suggest that we actually want to go one step further, and we want to interpret these results, because what I was asking myself was, well, if the whole point of this is that there are features that I'm not looking at, what features are contributing to the prediction of my laptop when I have a healthy image, like in this case, and what is the model focusing on when I throw at it a perturbed case? And the difference is quite notable. So in the first case, it's focusing on what it should. It's looking at the laptop, and it's looking at what I would look at if I'm trying to identify it, right? And in the case of the perturbed image, all that is completely lost, and it's actually looking somewhere else. So now you can understand why it's thinking this was a prayer rug. Now, if you're interested in playing with it yourself, I'm leaving here a list of tools that are actually extremely handy. They're all Python-based. And there's also a bunch of, there's a ton of collabs out there if you want to play around with it. Some of them are framework specific, but in any case, they're easy to get and they're fairly intuitive. Basically, you just import the attack, apply it on your model, and you can start playing around with it in no time. And in fact, if what you want to do is tweak them, the attack I was showing before, the fast gradient method, this is most of it implemented in less than 10 lines of code. So if you want to start around with it, yeah, take a picture, go there and have fun. So to recap, we've taken a look at what adversarial samples are. We've taken a look at whether we should care that much. And point being, yes, by all means, be aware that they exist, be aware that they will happen, and be aware that you might be affected, but focus on the basics first. And we've seen a couple of ways that you can apply the adversarial examples to robustify your models, basically breaking them and reporting how they were broken, and then exposing your models to them so that they become a bit more robust. So thank you very much. And if you've got any questions, shoot.
Thank you. I'll be taking questions if anybody has any.
So, in your experience, how much improvement do you actually get when training on adversarial samples? Because I can imagine, for example, in the first gradient approach, then there would always be sort of an adversarial gradient even after training on adversarial samples, right?
Yeah, something I didn't quite mention, but it's really important, is there's a factor called, what we call it epsilon, and basically when you generate, you don't just generate one single image out of that perturbation. You generate a whole range of them. And of course, the stronger that epsilon is, the bigger it is, the more perturbation you're adding, the more obvious it is to the human that the image has been tinkered with or tampered with. But of course, the effect is also much bigger in the model. Something that has been shown is that training on adversarial examples doesn't protect you from other attacks, though. So only applying the fast gradient method and thinking you're good is definitely not advisable. You need to cover all of the other attacks if you really want to be robust to them.
Was there a question over here? No. Okay. All right. Well, thank you very much for sharing your information. One more round of applause.
Thank you.